Hello students, in this video we present an interesting discussion about Simulink modeling of an electric vehicle charging station equipped with a battery backup system. With the rapid global transition towards electric mobility, the demand for fast, reliable and intelligent EV charging setup is increasing exponentially. Using MATLAB Simulink, we develop a detailed model that represents the complete energy flow within an EV charging station. The discussion begins with the grid interface and PV energy source, highlighting how power is managed under normal and distributed grid conditions. A key focus of this model is the battery energy storage system, which acts as a backup source to enhance reliability, reduce peak demand on the grid, and support uninterrupted vehicle charging during outages or load fluctuations. We also examine the power electronic converters used for AC to DC and DC to DC conversion, along with their associated control strategies. These controllers regulate voltage, current, and power flow to ensure safe and efficient charging of electric vehicles while maintaining system stability. Through Simulink plots and measurement tools, dynamic behavior such as load variation, state of charge changes, and transient responses are clearly observed and analyzed. This video is designed to bridge the gap between theoretical concepts and practical implementation. By the end of the session, viewers will gain a strong understanding of EV charging station architecture, control logic, and energy management using Simulink. Whether you are preparing for academic projects, research work, or real-world system design, this model provides a basic understanding platform for next-generation electric vehicle infrastructure. Let's begin the very basic discussion.
Welcome to this technical session on the modeling and analysis of a grid-connected, solar-powered electric vehicle charging station. In this lecture, we will examine the interaction between photovoltaic generation, power electronic conversion, battery storage, charging infrastructure, and the utility grid. The objective is to understand how each subsystem operates, how power is conditioned, and how control algorithms ensure stable charging under variable environmental and load conditions. Solar irradiance is the principal variable influencing the electrical output of a photovoltaic array. The power generated by a PV panel depends on incident irradiance, cell temperature, and module characteristics. As irradiance increases, current production rises, while temperature shifts primarily affect voltage output. Because these parameters fluctuate throughout the day, continuous power management is essential. PV generation is inherently intermittent. Weather variations, shading, cloud cover, and panel orientation lead to dynamic changes in available power. This variability necessitates robust DC-DC conversion, accurate tracking algorithms, and power flow control to ensure uninterrupted operation of the charging station. Renewable energy systems employ multiple converters and controllers to regulate energy flow between DC and AC subsystems. Since PV modules deliver DC and the grid supplies AC, bidirectional conversion becomes critical. EV charging stations require regulated DC for battery charging and therefore rely on converters that maintain stable output despite fluctuating PV input. Efficient coordination of power between the PV array, the grid, and the battery storage unit is essential to maintain reliable charging performance. The primary goal of this project is to design and simulate a grid-integrated solar charging station equipped with a battery storage system and controlled through a power electronic converter interface. The system must support EV charging, manage bidirectional power flow, and maintain grid compliance while maximizing renewable utilization. The system begins with the photovoltaic array connected to an MPPT, maximum power point tracking, controller. The MPPT algorithm ensures the PV modules operate at their optimal power point under changing irradiance and temperature. The PV array feeds a DC-DC boost converter. This converter elevates the panel voltage to the required DC bus level for storage charging or system supply. A charge controller is placed between the storage system and the load to regulate battery charging and discharging processes. It prevents thermal stress, over-voltage conditions, and deep discharge, thereby preserving battery health and extending operational life. When power is drawn from the grid, it is first processed through an LCL filter to attenuate switching harmonics. An AC-DC rectifier then converts the filtered AC into BC, providing a stable input for the DC bus and the charging system. Before selecting PV modules or sizing the array, we must determine the total system load that the solar installation is required to support. This includes identifying every electrical load, calculating its power rating, and determining how many hours per day it operates. From these values, we compute the system's daily energy demand in both watt-hours and ampere-hours, based on the operating voltage of the system. The load calculation process starts by converting each device's current draw into ampere-hours, multiplying it by its daily runtime, and then translating that into watt-hours using the system voltage. Once the overall daily energy requirement is established, we can estimate the size of the solar array needed to supply that energy during the available effective sunlight hours at the installation site. For this project, a Tesla Model Y standard range RWD is selected as the representative electric vehicle. This EV consumes approximately 3.82 miles per kilowatt hour, and this consumption rate plays a central role in determining how much energy the PV system must generate to support daily charging demand. This value helps translate driving distance into required electrical energy, ensuring that the solar array and battery storage are properly sized to meet the vehicle's charging needs. Now, let's understand how the perturb and observe MPPT algorithm works by looking at this power voltage characteristic curve of a photovoltaic module. This curve plots the PV output power on the vertical axis and the PV voltage on the horizontal axis. As sunlight conditions change, the operating point of the panel moves along this curve. The peak of the curve represents the maximum power point, or MPP, which is the optimum. Understanding the four regions. Starting from the left side of the curve. Region I. When we apply a perturbation and the resulting change in power is negative, while change in voltage is also negative, it means the operating point has moved farther away from the MPP. In this condition, the algorithm decreases the duty cycle to push the voltage back toward the optimal point. Region 2. Here, both delta P and delta V are positive. The system is still on the left side of the MPP, but the perturbation has improved power output. This tells the controller that it is moving in the correct direction, so the duty cycle is again decreased to continue approaching the peak. At the top center of the curve, the derivative dP divided by V becomes 0. This is the exact maximum power point, where any small change in voltage does not produce any change in power. Moving to the right, region 3. In this region, delta P is positive, but delta V is negative. The perturbation pushed the system toward the MPP, so the duty cycle must be increased to continue climbing toward the peak. Region 4. Here, the power change becomes negative, and voltage change becomes positive, meaning the system has gone past the MPP. The controller now increases the duty cycle to bring the operating point back toward the maximum power zone. The perturb and observe method operates using a simple feedback loop. It periodically perturbs, that is, slightly increases or decreases, the duty cycle of the converter. Then, it observes the resulting change in PV power. If the power increases after the perturbation, the controller continues in the same direction. If the power decreases, the controller reverses the direction of the perturbation. Only a few parameters need to be measured, mainly PV current and PV voltage, which makes the algorithm easy to implement, computationally light, and highly suitable for real-time control. The flowchart for this algorithm follows a clear sequence. Measure PV voltage and current, compute power, compare it with the previous cycle, evaluate the sign of delta P and delta V, adjust the duty cycle accordingly, and repeat this loop continuously. Through this iterative process, the system maintains operation very close to the maximum power point, even under changing sunlight, temperature, and so on.
This is the DC to DC boost converter. Here the Vs is showing the source voltage or the solar voltage. Here the solar arrays are connected. L is showing the inductor, the boost inductor. S is showing the control switch. This is actually the IGBT used in this circuit. And the D is the diode, C is the capacitor, and R is showing the batteries, the connected battery or the EV charging station. When IGBT is in on state, current in the boost inductor increases. Actually, when it is in on state, so it will flow in this form. The current will flow in this form, and that diode will be in off condition. When IGBT is off, the inductor will release the energy and the diode will behave like a short circuit. So these are the different formulas used in this discussion. The Faraday's law for the boost inductor is showing in this form: Vs into dt is equal to V naught minus Vs into 1 minus d into t. So the Vs is the voltage at the source voltage or the solar voltage. T is showing the duty cycle. T is showing the time duration. V naught is output voltage, and yeah, that's it. The DC voltage transfer function is showing MV is equal to V naught divided by Vs. So V naught will be greater than Vs, since it behaves like the DC to DC is showing is behaving like a boost converter. So it should be greater than V naught. V naught should be greater than Vs. The filter minimum inductance and the filter minimum capacitance value can be adjusted using these formulas, while the R is showing the load or the batteries connected at the output. So the inductance and capacitance values, we can randomly select these values. F is showing the switching frequency and R is showing the resistor. So resistor is not used, so we have only used the notation of the resistor. So we can randomly select these values. And the pi controller is actually generating the PWM of the signal. So where we will learn in this lecture in the model how we have used the pi controller. So a pi controller is actually a feedback control technique designed to regulate a system variable. There are two control signals, the pi and the integral. So the input is actually connected at the positive terminal and the feedback is connected at the negative terminal, and these will compare and output a comparative signal, a comparative or error signal. Then it will be feed into the pi controller, and the pi controller continuously compare the reference and measure signal, adjust the control signal, and ensure stable and fast tracking. So proper tuning of Kp and Ki are very important. So this is actually the UT is showing the output voltage, the Kp and Ki should be tuned accurately. The T is showing the total time period of the signal that is connected like a T on plus T off. So the duty cycle will be generated by turn on time divided by total period of signal into 100. And PWM is the modulation technique that will generate the variable with pulses to represent the analog input signal amplitude. So we will not moving in detail in this topic, but I will give you just a short overview of this topic. So it will generate the square waves with varying low and high pulses depending on the output signals, and these waveforms will contain high amplitude signal for on state and low amplitude signal for off state. So this is actually the pi controller, and it will generate the PWM signal, and we have used this pi controller in our model, in this Simulink model. So here the duty cycle is important to understand. Moving towards the Simulink model, we have used the irradiance, the temperature as the input variables. We can use the constant irradiance or the variable irradiance depending on our signals or our model. So the temperature here is used 25 degrees centigrade here. The solar array, MPPT controller, IGBTs, all these components are connected in this signal. This is actually the LC. LC is the boost converter. The first C is showing the capacitor just for smoothing. We have used it just for smoothing. And the C and actually the C2 is showing the inductor and C1 is showing the capacitor. So at this output, where the R was used, instead of R, we have used the battery storage, and in parallel, we have used the EV station battery. So the grid is connected at the other terminal, at the other side, where the LCL filter is also used for filtering, and the H bridge is just converting the single phase grid voltage or grid power to grid voltage to DC output voltage. So it will be connected at this terminal at the output of the solar array or at the input of battery storage. So it will behave like two-way two-directional mode. So the battery storage system is actually, this is the battery, and showing SOC is showing the state of charge of the battery, how much battery is charged, the current of the battery, and the voltage of the battery. So all these can be output at the scope. Here the LC are used for boost, and the two IGBT. This is actually, the whole circuit is showing this is a two-way, bidirectional DC to DC converter. This circuit is showing the pi controller. This is actually the pi control circuit, and it will generate the PWM. So these PWM signals will be inserted to these two IGBTs. So in this discussion, we will find the different components. It will actually, the solar array will contain the 20 parallel and 10 series solar panels. So grid is connected in line with solar array to supply continuous power at the connected DC bus. So this is actually a source, extra source if solar is not available. Then the grid will supply the voltage, the power. So moving towards the PV array. So there are 20 parallel strings and 10 series connected modules. Each module is generating 315 watt. The different parameters are showing here. The cells per module, open circuit voltage, short circuit voltage, voltage at maximum power point. So all these values are predefined. So we haven't changed any of these parameters. And the voltage at maximum power point will be 54.7 and the current will be 5.76. So these are the different parameters. Just look at the plot of each of the panel. Just look at for 25 degrees centigrade and 45 degrees centigrade. Let's find out how it will show. Here the graph is showing the current and the voltage, and the below power is power and voltage. So at 25 degrees centigrade, this is the waveform for 25 degrees centigrade. For 25 degrees centigrade, the maximum current will be supplied 115.2, while at the x-axis it shows 547. So if you look at this value, the voltage at maximum power point, it shows 54.7, and for 10 panels, 10 will be multiplied to this single voltage, and it will show 547. So for 10 panels, because the current is adding when the panels are connected in series. Sorry, the voltage will be added. Voltage will be added when the panels are connected in series. And for parallel panels, the current will increase. The power is showing 63 kilowatt. So each panel will generate 63 kilowatt. All these panels. 30 panels will generate 63 kilowatt, and the voltage will be 547. So this is actually for not for a single plot, but it's for the whole array, for the 30 panel array. So for a single panel, it will generate 315, and for 30 panels, it will generate 63 kilowatt. Just look at the MPPT. For MPPT, we have written a code that's showing the MPPT control circuit. So it's just a simple perturb code, and this is a very simple code. You can write it, and it's not difficult to keep it in detail, to discuss it in detail. So the initial limit and the limits are given for the from here the output will be the D, and this D will generate the maximum power point tracking. So it will give pulses to this IGBT. So it will be used for maximum power point tracking, and these values are not changed. These are the same as it is. I haven't changed any of these values. So the grid is a single phase 230 volt grid. Its frequency is 50 Hz, and it's connected at the swing bus. So the LCL filter is used just for smoothing of the waveform. So the H bridge values are also same. I haven't changed any of these values. I used the default values. So the VP is output of the battery, at the input of the battery. At these two terminals, battery is connected. So this is the bidirectional DC to DC converter, and the battery here used is a lithium ion. Voltage is 240. Its ampere hour is 50, and initial state of charge is it's initially 70% charge. So it will either charge or discharge. From here it will either start charging or discharge. And the PID controller is used here. Actually I have used the pi controller. This is a discrete time controller. It's a P and I values. I have used just random values. I randomly selected these values. We can even calculate these values from this formula. The 250, actually this value will be adjusted, and it will compare with the VP value. So the VP value is actually at the connector 1, connector 2. It's connected. It's the voltage between these 2 points, and it will generate these two will generate a PWM signal after the PWM generator. So its switching frequency and sampling time is adjusted, and this will generate a PWM signal that will move to this IGBT and in NOT form to the second IGBT. So either this IGBT will be on or the second one will be on using the NOT gate. The power flow can be either through this IGBT or through the first IGBT, depending on the switching. Because these IGBTs are just used for switching, just for behaving like a short circuit. It will behave like a short circuit. If it is on, it will behave like a short circuit. So it will adjust the power flow. So we are not going in much detail in this circuit, but just I want to give you a short overview of the model, how we have designed the battery storage system and the EV charging station. Its output waveform, just look at the output waveform. It shows the above 600 voltage. It's a voltage of above 600. It's almost 630 or 640, something around. So this panel will generate almost 630 something voltage. If you double click on it, we'll find in the plots the voltage at here in the 25 degrees centigrade. If you look at its the lower value, it shows 646. So it generated actually 646 voltage. 646 voltage it will be generated. And voltage at this terminal is also the same. It's almost the same, 646. So there is no error or there is no drop in this voltage. And the current of the grid is in this form. It's sinusoidal depending on the load, connected load, and it shows the voltage at its voltage output. Sorry, its current is out almost zero, and its voltage is 800 volt. Its fixed is almost same because it's showing the output of the H bridge, so it's in DC form, and it shows the zero voltage current. So actually the grid is not supplying any current because the whole voltage or power is supplied by the solar array. And also the battery storage is also 70% charged, so it will also generate some power to the EV station. It will create some power to the EV station. Just look at these plots. it shows that 70% is from 70% the battery is discharging continuously. So it will actually charge the EV station. And the first plot is showing the current and the lower plot is showing the voltage. So the current is almost above zero, nearly equal to zero, but it will be maybe 10 to 20 or maybe 100 ampere, and the voltage is fixed at 250. There is some jerk at the start, and when we look at the EV station, it's almost the same circuit just we have used in EV battery storage. So we fix it at 7% charge. So this battery is 7% charge, and it will be charging. Actually, from here it will start charging, and the current is just below the zero. It shows actually below zero. It shows the charging level, and the voltage is fixed at 250. So this both these batteries or both these stations are providing the same voltage, connected at 250 voltage. So this is the very basic circuit, and if you need any more information related to this model, you can write the comment and we will explain it in more detail. So I think it will be enough for you to understand the very basic of the EV charging station.